X-ray diffraction Bragg's law. W. L. Bragg's presented a simple explanation of diffracted beams from crystals. He derived the equation lambda is equal to 2d sine theta. Here d is the spacing between two planes having indices HKL, that is DHKL. This equation shows the scalar form of Bragg's law. Let us consider a real space planes the incoming wave is interacting with the planes as shown. A set of parallel planes. This is the incident wave and this is the reflected part of the wave. This is the incident part and the reflected part of the beam. This is actually not a normal reflection. But as a result, diffraction. But as a result of diffraction. So, the diffraction condition has to be satisfied. That is, the diffracted beam beams are found when the reflection from these planes interfere constructively. When the scatter wave aid constructively, bright spot will appear on the photographic plate. At this stage, the path difference will be equal to integral multiple of n lambda. The path difference from the figure can be calculated this distance is d. Let us draw a perpendicular from this side. This is A, B and C. This angle is theta while this is 90 degree. The path difference is equal to AB plus BC. From the figure, AB is equal to d sine of theta. Similarly, BC is d sine theta. The total path difference is d sine theta plus d sine of theta, which is equal to 2d sine theta. This is the condition for diffraction. When we consider a real space and the planar symmetry of the crystal, here n is equal to 1, 2, 3 and so on. Sine theta has maximum value at plus minus 1, so lambda is equal to or less than 2d. Here Bragg's law cannot determine the information about the bases, means atoms. Is defined the relative intensity and order of diffraction from given set of parallel planes. To find the scatter wave intensity, let us define a lattice translational vector T, which is defined as U1A1 plus U2A2 plus U3A3, where Ui are integers and Ai are the primitive lattice vector. Any local physical property such as charge density, electron number density, or magnetic moments is invariant under T, under the lattice translation vector T. The most important one is the electron number density, Nx, which is periodic, having periods A1, A2 and A3. Thus, we can use Fourier analysis to describe periodic function. The one dimension Fourier expansion for the Nx is n naught plus summation over p cp cos 2 pi px divided by a plus sp sine 2 pi px by a. In equation 1, p is integer, sp and cp are Fourier coefficient. 2 pi by a ensure periodicity, which is a point in reciprocal space. As we are switching from planar symmetry to periodicity, As we have earlier discussed for planar symmetry, the equation for the Bragg's law is n lambda 2d sine theta. The incident wave is interacting with the atoms, that is called basis. The diffraction is a result of periodic electron number density. The periodic electron number density will satisfy the equation at nx is equal to nx plus a. Let nx plus a is n naught plus summation p cos 2 pi p by a x plus a cp plus summation over p sp sine 2 pi p x plus a divided by a. This is equation 3. So nx plus a is n naught summation over p cp cos 2 pi p x by a plus 2 pi p plus sp sine 2 pi p x divided by a plus 2 pi p a divided by a is cancelled out, so 2 pi p. This is equation 4. Is cos theta plus 2 pi p means 2 pi integer is equal to cos theta, and sine theta is equal to sine theta plus 2 pi p. Thus equation for nx plus a will be equal to n naught summation over p cp cos 2 pi p x by a plus sp sine 2 pi p x divided by a. This is equation 5. So nx plus a is equal to nx. Thus 2 pi p by a is a point in reciprocal space. This means the reciprocal lattice point tells us the allowed term in Fourier series. This is x and this is nx. So the periodicity for the electron number density can be defined as in this manner. Here, this is the periodic arrangement and the periodic spacing A. In reciprocal space, if this is center point, this is 2 pi p 2 pi p by a. So for 1 this is 2 pi by a. This is 4 pi by a. This is 6 pi by a. Minus 2 pi by a. Minus 4 pi by a. Similarly, this is 6 pi by a. Similarly, we can write equation 5 as, which is the electron number density, summation over p np cos 2 pi p x by a. Here the coefficient n equation 6 are now complex numbers, whereas the electron number density is real. To show that nx is real, so np is equal to minus np, and that will satisfy nx is equal to nx steric. Let us take the complex conjugate of equation 6. So nx star will be equal to summation over p np e minus iota 2 pi p x by a. Iota will be replaced by minus iota. Our nx star is equal to summation over p n minus p star e iota 2 pi p by a into x. Here we replace p by minus p to sum over all p n minus p in this summation. Thus from equation 6 and 7, nx is equal to nx star, where np is equal to minus np star from these two equations. Expanding equation 6 in terms of p and minus p, that is np cos pi plus iota sin pi plus n minus p star cos pi plus iota sin pi. Expanding this equation in cos theta plus iota sin theta form, where phi is 2 pi px divided by a. So this equation defines that which is equal to the real function 2 real np cos phi. Thus the nx as real function is desired. The intensity of the scatter wave must be equal to ng square. Similarly, we can also find np from the equation as 1 over a integral from 0 to a nx e minus iota 2 pi p x divided by a into dx. Similarly, ng is equal to integral of the whole cell. This will be nr e minus iota g dot r over dv. So from this Fourier transform we can define or find the ng value.